We're going to continue on here with section 14.3, thermal expansion. So the change delta L in any linear dimension L sub naught of a solid object with a temperature change delta T is going to be approximately given this. The change in L is going to be equal to some coefficient here times the original length times delta T. You can also look at this particular formula if you divide both sides by delta T. The change in length divided by the change in the temperature is going to be some constant multiplied by this. Alpha, this coefficient here, is going to be called the coefficient of linear expansion. The change delta V in the volume of any solid or liquid material with a temperature change delta T is approximately this, where beta is the coefficient of volume expansion. So for many solids, beta is going to be equal to 3 times the coefficient of linear expansion. So here you can see you've got L naught, and then you've got the new length L at whatever temperature this was. Now we've changed it a little bit, and this delta L is showing how the length has changed. So you can see the new length is the old length plus the change, and then we're going to replace this with this formula right here. So let's take a look at this particular section. Okay. So most materials expand when their temperatures increase and contract when their temperatures fall. Bridge decks need special joints and supports to allow for that during the heat of the day. And of course, bridge decks contract back at night when it gets cooler. A completely filled and tightly capped bottle of water cracks when it is heated, but you can loosen a metal lid jar by running hot water on it. So those are all examples of thermal expansion. So you've got a rod here of length L sub naught at some initial temperature T sub naught. When the temperature changes by a small amount, delta T, then the length changes by delta L. Experiment shows that if delta T is not too large, say less than 100 degrees, 100 Celsius degrees or so, then the change in L is directly proportional to that change in T. Two rods are made of the same material, have the same temperature change, but one is twice as long as the other, then the change is also twice as great. So therefore, the change in L must also be proportional to the length, the original length. Introducing a proportionality constant alpha, and depending on the material, it's going to be different. We can express this relationship in an equation. So you can see those figures like we had covered before. You've got the initial temperature and then the change in the temperature, and then you see the change in the length. So you can see the formula that we had covered originally. The proportionality constant alpha is called the coefficient of linear expansion. If an object has length L sub naught at temperature T sub naught, then its length L at a temperature of T is equal to T naught plus delta T. It's going to be equal to this. And then if we go through and if we make our replacements here, we know what this is, and then we can rearrange the formula here to look like that. The units of alpha are in 1 over Kelvin or 1 over Celsius degrees. So this is going to be a temperature interval, and that's going to be the same regardless of which unit you use. The change in T is going to be your final temperature minus your initial. The value of alpha depends on the material and is usually found from a table. Delta L can be positive or negative depending on whether you're heating it up or cooling it down. So you can think of alpha as a fractional change in length of an object during a temperature change of 1 Celsius degree. For many materials, every linear dimension changes according to equation 14.4 or 14.5, in other words, these guys. Thus, L could be the thickness of a rod, the length of the side of a square sheet, or the diameter of a hole. Some materials, such as wood or single crystals, expand differently in different directions, and we're not going to consider that particular complication here. If we look at it on a molecular basis, we can picture this interatomic forces as maybe a set of springs that are in between these atoms. Each atom vibrates about its equilibrium position, and when the temperature increases, the average distance between molecules also increases. In other words, the atoms get further apart, and every dimension is going to increase. Biomaterial strips, although the coefficient of linear expansion may seem like a textbook concept, we do depend on it. Many instruments, including mechanical thermostats, which you may have in your own building, and some thermometers and circuit breakers, employ sensors made of a biomaterial strip. In other words, you take two different metals and you weld them together so that you've got the two materials forming two faces of the strip. You can kind of see that here. The photo shows a sensor that is using such strips to measure the temperature and humidity. In the temperature sensing coil, the two faces of the strip are made of metals with different coefficients of linear expansions. The change in temperature causes the strip to either coil or uncoil. In the humidity sensor, one face consists of paper or plastic that expands with increasing humidity, causing the strip to uncoil. In a mechanical thermostat, the coiling and uncoiling of a temperature-sensitive bimetallic strip makes and breaks electrical connections. So that's how you can tell your thermostat to turn on and turn off, so on and so forth. So when you heat an object that has a hole in it, the hole gets bigger. So you can see that going on right here. If you heat a flat plate of material, its area increases. If you now cut a section from the center of the plate, both the cutout and the remaining plate behave as they did previously. The cutout piece and the hole it came from both get bigger. The direct proportionality between delta L and delta T isn't exact. It's approximately correct for sufficiently small temperature changes. For a given material, alpha varies somewhat with the initial temperature and the size of the temperature interval. Average values for those materials are going to be displayed here. Within precision of these values, we don't need to worry about whether the initial temperature is 0 degrees Celsius or 20 degrees Celsius or some other temperature. It's usually a very small number. Even for a temperature change of 100 Celsius degrees, the fractional change in length is, 1/1000, so it's not that much. But the expansion of a 100-meter bridge by 0.1 meters has to be taken seriously. Obviously, you don't want cars falling in through holes and things of that sort. Volume expansion. If you're looking for both solid and liquid materials, you can have volume expansion. If the change is not too great, then the increase in volume is approximately proportional to the temperature change. The change in volume is also proportional to the initial volume. So just like what we had with the linear expansion, we've got that here with the volume expansion. The only difference we're seeing here are the V's as well as the beta. And we can see those changes here. Here again are some more coefficients of volume expansion. The units are the same as what they are for the linear expansion. For solid materials that expand equally in all directions, there is a simple relationship between the volume expansion coefficient and linear expansion coefficient. And there is the relationship. So above 4 degrees Celsius, liquid water expands with increasing temperature. However, between 0 and 4 degrees Celsius, water decreases in volume with increasing temperature. So in that range, the coefficient of volume expansion is negative. Thus, water has its greatest density at 4 degrees Celsius. The anomalous expansion of water in the temperature range from 0 degrees Celsius to 10 is shown here in this figure. But water also expands an additional amount when it freezes. That's why ice humps in the middle of the compartments in an ice cube tray, and why pipes full of water burst if they're allowed to freeze. Most other materials contract when they freeze. This anomalous behavior of water has an important aspect on plant and animal life in lakes. When a lake cools, the cooled water at the surface flows to the bottom because of its greater density. But when the temperature goes below 4 degrees Celsius, this flow ceases and the water near the surface remains colder and less dense. As the surface freezes, the ice floats because it's less dense. The water at the bottom remains at 4 degrees Celsius until nearly the entire lake is frozen. If water behaved like most substances, contracting continuously on cooling and freezing, lakes would freeze up from the bottom up. Circulation due to density differences would continuously carry warmer water to the surface for efficient cooling, and lakes would freeze solid much more easily. This would destroy all plant and animal life that could withstand the cold water, but not the freezing. All life forms known on Earth depend on chemical systems based on aqueous solutions. If water did not have this special property, the evolution of various life forms would have taken a very different course. So, if we clamp the ends of a rod rigidly to prevent expansion or contraction and then raise or lower the temperature, a compressive or tensile stress called thermal stress develops. The rod would like to expand or contract, but the clamps won't let it. The resulting stress may become great enough to strain the rod irreversibly or even break it. Concrete highways and bridge decks usually have gaps between sections filled with a flexible material or bridged by interlocking teeth, like what you see here. That prevents expansion and contraction of the concrete, or permits expansion and contraction of the concrete. If one end of the steel bridge is rigidly fastened to its abutment, then the other end usually rests on rollers. So to calculate the thermal stress in a clamped rod, we compute the amount the rod would expand if it were not held, and then find the stress needed to compress or stretch it back to its original length. So let's say we've got a rod here of this length in a cross-sectional area held at constant length while the temperature is reduced, causing a tensile stress. The fractional change in the length of the rod, if it were free to contract, would be this. This is negative and that is negative. So the tension F must increase enough to produce an equal and opposite fractional change in the length. So from the definition of Young's modulus, we turn that around and this is what we have. If the total fractional change is 0, then this plus this is going to be 0, or the force is going to be equal to this. For a decrease in temperature, that is negative, so the force is positive, and the tensile stress of the rod becomes this. And obviously, if this is positive, then that is negative, corresponding to compressive force and strength.